going to begin. They're going to see us talking for a little bit.
Okay.
Cool.
Well, welcome to the exam preparation live stream for 1131 and 1141. So we'll start by doing some 1131 questions from last year's 1131 exam, and also we'll do some 1141 questions at the second half of the live stream.
Yeah, so if you are only interested in the harder stuff, it's going to be towards the end of the stream. Good, and a big shout out to all the people having parties out there. So hello, please say in the chat if you are having a party. I'd like to hear about it. And I don't know, can they send photos in the chat? I don't know. They might be able to send links to photos. Okay, if you can do that, that would be awesome, because I'd like to see it. Anyway, Josh, you're up first.
All right. So our first question is, it's a fairly common question to turn up. We want to state what the mean value theorem is, and then we want to use the mean value theorem to prove an inequality. So it's a fairly standard question to turn up in a test or an exam. So let's just firstly do part 1. So if we have a function f which is continuous on the interval. Actually, I'll make this a bit more explicit. I want to say on the closed interval AB, and differentiable on the open interval AB. So same interval, but I'm not including the endpoints. So, well, what the mean value theorem says is that we can guarantee there'll be some value C, and this C will be in the open interval, such that such that the derivative at that point is the same as what you would get if you just calculate the slope from the line from the A to B. So this is what you might think of the mean slope. That's where the mean sort of comes from. And this is the slope at a particular point. So there's guaranteed to be a point in that interval which has this mean slope. And every part of what I wrote down I think is essential. It does need to be continuous on the closed interval. It does need to be differentiable on the open interval. And this is the conclusion. And again, open interval here. So before I rub this out, any comments?
Yeah, I'd just like to add a little bit of interpretation to this. You can hold that. What the mean values theorem is telling you is really how far, if you think of A being fixed, how far away can f of b be, if you like? You have some, I like to think about it as estimating the difference between f of b and f of a. How big can it be? Well, it's going to be it's going to be bounded on the difference between b and a, and the bound will end up being the maximum derivative here. And this is essentially the kind of scenario where you want to be using the mean value theorem. So here it's telling me, this is classic mean value theorem stuff. Here's the function, and I want to get some kind of bound for it in terms of the inputs to that function. And it's going to depend on the derivative. So that's the way I like to think about it. So if you like, you've got some prisoner escaping from camp, and f of b, his prison camp, and f of b is how far away they are from the camp. And this difference here is time, and this here is how fast they can go, the maximum how fast they can go. Of course, they might go slower, but you can get the distance between where they are right now and where they were originally as the maximum of how fast they go times by the amount of time they have. So this is classic mean value theorem stuff. Okay. Sorry, go on, Josh.
All right. Yeah, so that inequality will come up in the next question. So I didn't actually mention the inequality here. We didn't. The theorem itself just tells you the existence of this point. But yeah, if you can if you can work out the largest this can be, you definitely know how big this can be. And that's what we're going to use in the next step. So I think I will run out the entire thing, so I do need space. Now, these inequality questions, they're usually fairly standard in the way you set them up. So I need to have my continuous function, my continuous differentiable function, and it's going to be this sign here, and I need the interval. So I'm going to let my function, so let f of t equal sine of t. So that's my function, and my interval, so let f be this, and our interval is going to be the interval from 0 to x. So I'm only looking at considering really t values in this interval. So this is my a, this is my b, and this is my function. So what does the mean value theorem say here? So maybe I should make sure I'm satisfying it just by restating the conditions. So since f is, well, it's continuous everywhere. It's actually continuous over all the reals, including this one. It's also differentiable everywhere. There's no real restriction on this. What does the mean value theorem say? Well, it says that f prime of c will be equal to the sine of x minus the sine of naught over x minus naught. And I guess maybe I should have calculated this before, but the derivative of sine is just cosine. So we have that for C, some C. In the interval 0x. So that's what the mean value theorem is telling me, and why this is useful. Well, firstly, this is just 0. So I have that sine of x over x will be the cosine of c, for some c in this range. And here I'm just going to use the fairly simple fact that I know cosine is always bounded, is always less than 1. So that this quantity here must be less than 1. So this quantity being sine of x over x. So since the cosine of c, the worst that could be, well, that's always less
than or equal to 1.
Yeah, less than or equal to 1. So the question does say less than or equal to. So since that's always true, we have that, well, this is always less than or equal to 1, so this is always less than or equal to 1 because it's equal to it. So since we have that, the sine of x over x is less than or equal to 1. And that's fairly close to what we want to prove. I just would like to bring this x onto the other side, and I have to here use the fact x has to be positive for this to work, otherwise I'll flip my inequality. So because x is a positive number, so it is important that x be a positive number, multiplying by x just gives our inequality. It gives us that the sine of x is less than or equal to x. And that's only for x greater than or equal to 0. That's from camera, I think.
Cool. Yep. Perfect. So this is a very satisfying application of the mean value theorem. I can see that Josh is checking the conditions of the mean value theorem. So he's making it really clear. This is the function, this is the interval, and the, I guess, prerequisites of the mean value theorem are satisfied. It is a continuous function that's differentiable everywhere. I'm really pleased that it's stated. And then it's just classic stuff. I mean, this function is bounded by this derivative here, which is at most 1, so it just falls out. Great.
Okay.
I should mention, there's, in case you're panicking right now, Josh and I have only picked out the hard parts of the 2016 exam. So there's loads of easy parts of that exam that we're not covering. We're just deciding to cover the things that we think are hard and the things that we think haven't yet been covered by, say, a class test. So we're really focusing on the stuff that's not been covered in class tests and the stuff that is actually hard, like this. So if you are concerned about what you see here, it's,
yes, we did start at question 2.
yeah, we missed all of the easy stuff. There will be loads of kind of easy questions in your exam. Oh, maybe I should make a little mention of some good exam strategy. When you get into the exam, it's a 2-hour exam, there are 4 questions. So one thing I used to do when I was sitting exams is just write at the top of the page how long I have to complete this question. So if it's a 2-hour exam and starting at 1 o'clock, then I'd write 1:30 on the top of page 1, which means that by 1:30 I need to just finish whatever it is that I'm doing on this page and move on. This is question 2. I might write 2 o'clock because that would be the time I must absolutely finish this page. It's time to just put it down and leave it. Whatever you've not done, it's finished. Move on. And that way you can actually devote time proportionate to how the exam is marked. You need equal time for equal marks essentially, and that's the best strategy to getting. I think the best strategy to getting good marks. So yeah, just a little note. You might like to put on. Let's see. We're doing question 2, and it's now 20 past. So I might say that this is going to be 1:50. So this kind of indicating when I'm just going to tear this down and move on. Right. So back to the question. My question. Sketch the polar curve of this on some range. All right. These questions are somewhat difficult. There's lots of ways of doing them. I'm going to show you my favorite way of doing them. And the first thing is to just put on some easy values of theta to just try and figure out where what this thing is actually doing. So remember that we're actually sketching the points r cos theta, r sine theta, subject to the restriction that r is 1 minus cos theta, and theta is allowed to range like this. So this is what we're actually trying to sketch. So I'll put in some values of theta on a little table, and I'll just choose really easy values. 0, pi on 2, pi, 3 pi on 2. Just really easy ones. I just want to plot a few points to know I'm in the right ballpark here. Cos theta, sine theta. You don't have to write these in, but I find it might be helpful. Cos theta is cos theta going back to 0. Good. And maybe I will include 2 pi. And this comes back to 1, and this comes back to 0. Good. And okay, so what's r? What are the r values? The r values are, well, 1 minus cos theta, so that's 0. When 1 minus this is 1, 1 minus this is 2, 1 minus this is 1, 1 minus this is 0. Good. And now I've got r, cos, and theta. I'm in a position to talk about my x, which is this thing, and my y, which is this thing. So x, just being r cos theta, is that times that, that times that, that times that, that times that, that times that. And y, just being r sine theta, is that times that, that times that. Sorry, that times that's 1. That times that, minus 1, 0. Good. So at this point, I can start trying to get a picture of what's actually going on here. And I'm just going to populate this picture with some stuff. So what are my points? My points are 0, 0, so I know it goes through this. 0, 1, I know it goes through here. Negative 2, 0. And 0, minus 1. Good. So this is, how do I connect these dots? That's a good question. But at least I have some dots, all right? And maybe I can even annotate my graph. That's 1, minus 2. And of course, that's the origin. Right. This is a good place to start, but I need to kind of do something to figure out how to connect all these dots. What I'd really like is the derivative, but I don't have necessarily the derivative dy dx. But I can get at bits of it. I can get at dy d theta fairly easily. So since y is just equal to r sine theta, which is 1 minus cos theta sine theta, I can figure out what so I can express y just in terms of theta. I can figure out what dy d theta is. Is equal to, well, I can differentiate this with respect to theta. Cos goes to and this times this causes sine. So this is equal to sine theta. Okay, so this is sine theta is 1 minus cos squared theta. And I'll just express it in terms of causes minus another cos squared theta plus cos theta, which is equal to negative 2 cos squared theta plus cos theta plus 1. Okay, so this is the derivative dy d theta. Now, I want to know when is this 0. Now, when this is 0 is going to tell me when my function is horizontal. Remember, this is dy d theta, and maybe I'll just write it down. When dy d theta is equal to 0, function. So I want to set this equal to theta and figure out what, set this equal to 0 and find out for which values of theta do I get something horizontal. Well, it turns out that this is just a quadratic, right? So I could solve this dy d theta equals 0 when cos theta, it's quadratic in cos theta is equal to just minus minus 1 plus or minus 3. Which is either minus 1 or 1 half.
Should it be 1?
Should it be positive 1? It should be positive 1. Yes, thank you. Or minus a half. Thank you. Good. So cos if cos theta is equal to 1, then theta is equal to... I've gotten rid of my diagram. Cos theta is equal to 1 means theta is equal to 0, or 2 pi. And if cos theta is equal to -1/2, then theta is equal to 2 pi on 3 or 4 pi on 3. And this is telling me when my function is flat. Okay, so this might be a bit tricky to solve, but it's telling me when my function is flat. So it's flat when theta is equal to 0, which is this point here, and when theta is equal to 2 pi on 3, so if I rotate around by 2 pi on 3, somewhere, say, up here-ish, and somewhere down here. You can't see that, can you? Damn.
Over the camera?
Can, yes please. Somewhere down here, say. So there's some point here with argument 2 pi and 3, and some other argument here with some point here with argument 4 pi and 3. I don't exactly care where it is, I'm just pointing it out. And similarly, I want to find where d theta is equal to 0. And these are going to give me my kind of points where the derivative dy dx is undefined. Since x is equal to cos theta is equal to then dx d theta is equal to, now I can do this, d which is equal to, this thing, cos goes to negative sign, so this is sine theta cos theta, and this one is cos theta times negative sine squared, so that's minus sine theta plus cos theta. Is that right? This doesn't seem right. I think I've done something wrong here. And I think these two things are supposed to cancel specifically. Maybe I'll just do it again slowly, because I think I'm doing something wrong here. So cos goes to negative sign, which means this is positive sign. Plus this one. No, it still gives me the same thing. What am I doing? I did this before, and I know it's supposed to be sine theta. Well, at least I think it was sine theta.
If it was sine theta, what would the answer be then? You'd have sine theta being, you want to
sine theta 0 at 0 and pi, which gives me that one. And no, wait, it's not, because that's not it's supposed to give me other answers here and here. So maybe this is correct. All right, I'm just going to have to roll with it as if it is correct. So I guess 2 sine theta cos theta. Oh yeah, no, this is fine.
Yeah.
Sine theta. Sorry, I'm just going crazy. Sine theta 2 cos theta minus 1. So how can I make this equal 0? Well, either when sine, so this is equal to 0, well, maybe I'll write something first. When you've got this thing being equal to 0, you've got these kind of vertical points. And this occurs either when theta is equal to, sine theta equals 0, then theta is equal to 0 or pi. So I've got these kind of vertical points here. So this is both horizontal and vertical, which is telling me there's something crazy going on here. Or this one. Or when 2 cos theta is equal to 1, so cos. Or when cos theta is equal to 1/2, which happens, say, here and here. And now now I can actually draw this thing. There's my orange. I've got some kind of idea about what's going on. Function's going to be kind of flattish here. Well, it has to be kind of vertical here. Let's start here. This is going to be a problem. It's going to go up. At some point it's going to be flat, as in have a kind of vertical asymptote. And then it's going to come around and go through there. Maybe I'll move that down a bit. It's going to be flat, come up. And then it's going to have to be, vertical. And then it's going to be horizontal. And then it's going to come down and be vertical again. And then it's going to come down and be horizontal. Pass through here. Move that in. Be horizontal here and come back. I know I've got problems here because the derivative is supposed to be both flat and both horizontal and vertical. So this is going to be a problem. Then that's fine. It's clear that the derivative is not actually defined at this point. Oh man, the polar questions are hard. You have to do quite a bit to get a good picture of what this is. Again, adhere to the strict time limit. Realistically, this is probably a 3-mark question, maybe 4 marks. Do not spend all your time doing it. Josh, advice?
Yeah, so for this sort of question, I mean, yeah, the more information you look for, the higher quality your plot will be. But there is a diminishing return on your time. For me, this would have taken a while to get these numbers, to get these exact places where this was going to be. It does add a lot of quality to your plot, though, because it's very hard to know what's going on here until you actually work out that there is a real problem in both derivatives. It's saying it's both flat and horizontal.
Your dy dx is essentially 0 over 0 here, and you've got real trouble with it.
Yeah.
And look, I don't want to go into any more detail about it than that.
Yeah.
Because it's realistically a 3-mark question.
Yeah. Another way I would probably, just because the function was so simple to begin with, what I like to draw first for myself is how this looks in theta space. So
you might be off the board here, so why don't I just rub off what I've got and you can draw it.
So this is, I guess, maybe the way I usually think about it. This is pretty similar to what Daniel was doing when he had his table of values. Maybe the table of values is a bit cleaner. I sometimes like to look at how this looks in R theta space, because this is just the cosine function, which is flipped upside down and shifted up by 1. It doesn't take me too long to work out. It does look like this, from 0 to 2 pi. So I've taken, this is 1, this is 2. So in terms of R theta, I know sort of what's going on with these two variables. I can see it's going to start with a very small r, it's going to shoot out to 2 here at pi, and it's going to come back down to 0. So that's how I would sort of look at my plot. It's not really telling me anything about the derivatives in the x or the y direction. It doesn't help you get those. You'd have to do some algebra to actually solve for those. But when I'm looking at this, I'm sort of getting an idea in my head what this curve looks like. I know it does start here. It will. Let's see. I guess I could. Yeah, we'll just shoot out, and it will be maximized here at 2. So my radius is now 2, but I'm at pi, so that's over here. But I don't get much information that I just know it's sort of coming like that. And anything until I look into it, anything could be happening there. Yeah, so as an alternative to making a table, you could also make plots like this to get in your head what's going on with r and theta. But the plot they really want is the plot in the xy space. So you'll have to somehow translate that into x and y. Coming close to 0 is always a bit of a problem when you're having these plots. So that's my only advice I could give for this one, is maybe a plot like this will also give you some information.
There are other ways of doing it. That way I showed you is, I think, my favorite way, but it takes a long time.
Yeah, definitely gives you a high quality plot.
Yeah, but at this point we should probably move on, modeling good behavior and telling people to abandon the stuff abandon it. And look, if you get time at the end to come back to it, great, that's great. But make sure that you're vicious with your cutoffs when it comes to time, because you don't have 10 minutes to spend on a 3-mark question necessarily.
Okay. So the next question, move the camera back. Okay, thank you. So the next question is really to find the derivative of this. This is part command, part hint. It says use logarithmic differentiation, which is just use the fact that you know what the derivative of the natural log is. So to do that, well, we're going to rewrite this exponent rather than a power of 2 as a power of e. This is part 3. So I'm looking for dy dx. I'm looking for the derivative of, well, I'm going to rewrite this 2 to the sine x as e to the log, e acting on log 2 to the sine x. Because I understand e and I understand log, and because of the log laws, I can pull out this sine, make it a bit simpler. So I'm really trying to find the derivative of e to the sine x log of 2 times log 2. So this is a fairly simple application of the chain rule. I know what the derivative of the exponential is. The derivative of the exponential is just itself. So this will be just the exponential of sine x log 2. But then I need to, by the chain rule, take the derivative of sine x times log of 2. And I might just put a reason to be clear by the chain rule. Well, log 2 is a constant, so this is really just the derivative of sine. Derivative of sine is cosine. So this is e to the sine x log 2 times derivative of sine is cosine, so the cosine of x times e log of 2. Now that is correct, but I feel like I could repackage this one up just to make it a little bit nicer. I know what this was. This is what I started with. It was the 2 to the sine x. So I might just write this as 2 to the sine x times the cosine of x times the natural log of 2. And that's my answer. Comments?
It's nice. It does what you're supposed to do. I wanted to do this differently and just take the logs of both sides and then use and then just take the derivative. I'm not sure if that's permitted or. Would that be considered logarithmic differentiation?
No, it seems to fit the bill.
Maybe.
Would you like to do that?
Yeah, I'd like to do that. Let's hope I get the same answer. So, starting off with y is 2 sine x. I'll take the natural log of both sides. Sine. And then I'll differentiate both sides with respect to x. And I can just do that one sine, that's... I still have some work to do here. I haven't actually taken the derivative of this one. And it's, I need to use the chain rule to do that. So really I should be writing, instead of, I'll keep it as d, dx. But this is equal to dy dx times ln times d dy, which is still equal to cos x. That's, I mean, this is just rewriting the left-hand side with the chain rule. This is what I wanted. This is 1 on y, so dy dx times 1 on y equals cos. And then I can take the y up there and relabel it as 2 sine x. So remember, y is just 2 sine x, so I'll write it as 2 sine x times cos x ln 2. Which is what you've got, I think.
Yep.
Cool.
Yes, so that should happen. If you use a correct technique, you should get the same answer.
Or an equivalent answer.
Yes.
Alright. A matrix, good, some algebra, calculate a determinant, and do some other stuff. Right, there's lots of ways of calculating a determinant, you know all sorts of ways. I'm going to choose expanding along a column, and the reason I'm going to do that is because I see this has a lot of zeros in it. So when you see a matrix that has a lot of zeros in it, choose to calculate the determinant by expanding along that row or column. So determinant of A is equal to, again, I'm going to expand along this column, which will give me 1 times this matrix, 3, 8, 2, 6. Determinant, so I'll write it like this. And then I alternate the sign and go 0 times the determinant, 1, 4, 2, 6. Plus 0 times the determinant, 1, 4, 3, 8. And I hope you can see that all these two terms were just overkill anyway. In fact, I didn't need to write them down. Can they see that?
Yep.
I didn't even need to write them down because they'll be 0 anyway. So that will go because I've got a 0 here. That will go because I've got a 0 here. So, don't even bother writing them down. This will just be 1 times 12 minus 16, which is minus 2. Determinant of A is minus 2. No, not 12. That's 18 minus 16. Positive 2. 18 minus 16. Yes. Positive 2. Right. Does A have an inverse? So this was part A. Does A have an inverse? B. Yes. And you probably need to give some reason for this. Even if it doesn't ask you for a reason, give a reason. Yes. Since det A is not equal to 0. Whenever the determinant is not 0, there is an inverse. It's a nifty way of determining if an inverse exists without actually explicitly finding it. And C, write down det of 5A. Now you need to remember how row operations actually affect the determinant. If I multiply this row by 5, then that multiplies the determinant by 5. Oh. it multiplies the determinant by 5. If I multiply this thing by 5, that multiplies the determinant by 5, and if I multiply row 3 by 5, that multiplies the determinant by 5. So in all up to scalar multiply a by 5, that is 3 row operations. This one, and this one, all of which affect the determinant. So det of 5a is equal to 5 cubed times the determinant of a, which is 125 times 2, which is 250. Determinant of a is actually 250.
So that's nice. And yeah, they've been very kind to you with this one. They picked out a column, trying to make it obvious. I want you to expand upon this column to find the answer. And I think this is exactly how you should answer part C. I mean, technically you could just multiply this by 5 and do it, but that would be time wasted. Because you should just automatically know that you've scaled all the rows by 5. That's 3 factors of 5 you need to take care of.
Yeah. So,
I mean, it would be correct to do that, but you would have lost a bit of time you could have used up elsewhere.
yeah, back on that polar form question.
Yes. Okay. Alright, so this next question is to sketch the hyperbolic cosine of x as well as its inverse function and put them on the same set of axes. So, just in case we've forgotten, it might be a nice idea just to write this out in the definition for this in terms of the exponentials. So this will help both you, or will help you, I think. So, if you're looking at the hyperbolic cosine of x, that is e to the x plus e to the minus x over 2. It's the average of these two exponentials. So if I wanted to plot that, I think for this question it is just fair to make a plot of what you know about this function. You could put in some values to check. For example, if I put in 0, I get e to the 0 plus e to the 0, that's a 2. A 2 over 2 is 1. So it does pass through the value 1. It is the sum of two exponentials. So on this side, one of them doesn't contribute very much, and you just get pretty much the other exponential. And on this side, you have this exponential. So this is x, y, and this is a plot of y equals the hyperbolic cosine of x. Now we want to plot the inverse function. So when you're plotting an inverse function, a really easy way to think about it is you're just taking your original function and you're reflecting upon through the line y equals x. So I'm just going to take my same plot and flip it over. That wouldn't give a function though if I just drew the same curve over here. One thing you have to understand is that when you're looking at the inverse of the hyperbolic cosine, you're only picking the positive values. You're only picking those values with a positive. Only picking out the positive values. So it's the same plot, but I have to cut it off here at 1. And then you have that same plot. And, well, from experience, I know that these two don't touch, just because I've sort of played around with these before. So that's the plot I would give. This is a plot of y equals the inverse of the hyperbolic cosine. And I actually think that would probably be sufficient for this question. What do you think, Daniel?
I'd give that the marks.
So yeah, I think one of the important things is it is only defined for the positive value. So don't draw both of them, you'll lose marks for doing that.
Yeah. I think it's typical to see a question on hyperbolic cos and sine in the exam because it hasn't been tested before. But the question will be really easy, like sketch it. Or just know what the definition is and work with that. So you should expect to see something about hyperbolic cos and sine because we haven't tested you on that yet. But it should be a fairly routine kind of question.
Okay.
Cool. Next one. Okay, so here we have some integrals, and you really have to keep your wits about you with these integral questions. You have all these different methods of evaluating integrals and determining if they converge or diverge, and you need to decide which method to use. So for part A, I look at part A and I think I can integrate that. That seems all right. Here I have a function. Here I have something that's like its derivative. I'm just going to see if I can integrate it. So for part A, let's call this I equals and I'm going to make this look more and more like, well, I want this to look like the derivative, and the derivative of negative 2x is, the negative x squared is negative 2x, so I want the integral negative 2x, which means I divide by negative 1/2 e to the negative x squared dx 0 to infinity. Good. And this is the kind of thing I could do by substitution, right? Let u be equal to negative x squared. Let u equal negative x squared. Then du is negative 2x dx, which I can have, and when x is equal to 0, when x is 0, u is 0, and when x is equal to negative infinity, u is equal to positive infinity, u is equal to negative infinity. So I can make a substitution here. I have I is negative 1/2 times the integral from 0 to negative infinity of e to the u du. Right, now I'm in good shape to actually do something. The negative infinity here is somewhat troubling. This is an improper integral. I haven't got a number here, I've got negative infinity. So I'll write this out as a proper integral. Lim r goes to negative infinity, the integral from 0 to r e to the u du. Right, now this is proper. Well, it's a limit of proper integrals. And I can actually do this. Integrating e to the u is the best possible thing to integrate. That's just e to the u from 0 to r, which is negative 1/2 e to the r. Oh, I forgot my limits. Damn it. So what is this? E to the r, negative infinity minus 1. And as r goes to negative infinity, this goes to 0, so I just end up with 1/2. At this point you can say, yes, it converges, and in fact, it's a half. So the area under this curve is in fact finite, and which is what it means for an integral to converge, and we can even say what it converges to. Josh?
Right. So yeah, I like this. There's one thing in me the pedant doesn't like, and that's the equal infinity part. I probably personally would write this that as x tends to infinity, u tends to minus infinity.
Yeah. Or even make the r substitution up here.
Yes.
That might have been even better. Cool.
Personally, I never like to see anything equal to infinity. It's always something you're approaching. So I like to see as you're approaching.
Thank you. I accept the constructive feedback. All right. Dun, dun, dun. For integral b. Integral b is not so easy. Well, I can't evaluate it explicitly, but I can kind of eyeball it and see, this is something like 1 on x to the 3. I mean, if x is large, say, then this is, I can ignore the 1, and this is like saying 1 on the square root of x to the 6, which is almost x to the 3. And in fact, this is bounded by 1 on x to the 3 because this is just a little bit bigger than 1 on x to the 6. So I'm thinking I should compare this to 1 on x cubed, and in fact that comparison will be fairly easy because this is just a little bit smaller than 1 on x cubed. So maybe I'll start off like this. What I want to say is that 1 plus x to the 6 is less than or equal to 1 on x cubed. This is what I want to say. And I'm giving myself some space because I need to justify this statement. I can bring that up there and that up there, choosing x values to be positive. Since my x's are bigger than 0, then this won't change the inequality, and this gets to be x cubed is less than or equal to. So maybe I'll say since just to justify the fact that the inequalities haven't changed. And now I can square both sides. X, again, using the fact that x's are positive. And now, since. And when, as a marker, you're reading this, you're just impressed by the students' godlike foresight, because they start off with something very trivial, like 0 is less than 1. When I see that, I think, all right, where are you going with this? And then, just by magic almost, they come up with this inequality. It looks amazing, but in reality, you've just done it backwards. But that's not, the marker can't distinguish between your absolute genius and just doing it backwards when you do it this way. So since this is bounded by this, then I can integrate both sides, and I get that the integral between 0 and that which you can say is finite by the p-test. And hence it converges. Josh.
Yeah, I mean that seems correct to me. We should qualify exactly what it was about the p-test that did this. So I might, if I want to make sure that I really understood the p-test, was for the p minus 3 or p was 3. Because in this case, the power you have here, this p, is greater than 1. If that were equal to 1, you don't get convergence anymore. Yeah. But this is fine. It is by the p-test, this is a cube. You know those things converge. By the p-test, the integral does converge. And this is very nice. It's very nice to, when you pick up a student's test, I look at this and go, wow, yeah, that's true. So I have no idea that it was actually constructed backwards, as a lot of things may be, actually. Yep, so I'm happy with this.
Cool.
So there are actually two ways I can think of doing this problem. And I do wonder, so I might actually do it the way that first jumps into my head when I see this problem, but it may not actually be the best way to do this problem. But it's good to be able to fall back on the tools you do know if you've sort of forgotten some facts. So here, I want to prove that this limit is just e to the 3. And when I look at this, my first instinct is this is something to the power of x. We've been learning about logs and exponentials in this course. Let's rewrite this in terms of other things which I really do understand. So we can write the limit. So I'm looking at the limit as x goes to infinity, and I'm just going to rewrite it now. It's 1 plus 3x dx, and that is the same as the limit of e, and I'm going to, when I apply the log, I'm going to use the log law straight away to get this as e to the log x log 1 plus 3x. So I'm trying to force the problem into a different problem which I think I understand a bit better. So I'm looking at this and I'm thinking, well, x is tending to infinity. And the log, well, the log is going to the log of something, and this thing here is tending to 1. So you're ending up with infinity times log of 1 being 0, infinity times 0. This is one of the candidates for L'Hopital's rule, but you do need to do a little bit of work to rewrite this. So I might just also state that this is, if I want to rewrite this in a slightly different form, it's the limit as x goes to infinity, e to the log 1 plus 3 over x over 1 over x. So I haven't changed anything. It's still the exact same problem. These things are just all the exact same equation written in different ways. But I think I can get a handle on this one using L'Hopital's. So let's check that, because L'Hopital's rule, it wants me to verify first the limit exists before I actually use it. So we write that, and note the following, that the limit as x goes to infinity of the derivative of log 1 plus 3x over the derivative of 1 over x is the same calculation as calculating the limit of, so a little bit of work, you need to, this is not the prettiest thing, but it will work. When I take the derivative of the log, I get a 1 over 1 plus 3 to the x. When I take the derivative of what's inside, that will give me a minus 3 over x squared, and the one on the bottom is just minus 1 over x squared. Which is nice, because there is a cancellation here. This and this will cancel out. You might want to rewrite it algebraically first, but that will cancel out. You'll also get these minus signs cancelling out. So for this thing, this is tending to 1 over 1, 1 over 1 times 3. So this is just equal to 3. So I know that, well, because this does tend to 3, this also tends to 3. Now, to be very precise, since e to the x is continuous at x equals 3, well, we have that this thing we were looking at, this limit as x goes to infinity of e to the x log 1 plus 3 x. Well, this is continuous at the limit of this thing, so this is just going to be the same as taking the limit inside the function. And that's just equal to e to the 3. I'm going to be a little bit cheating to say by above. I don't think anyone who marks this would disagree.
Yeah, I'd say that's fine.
So this is one way to do it. There is another better way to do it, and I believe Daniel will show us. This is the first thing that jumped into my mind, was to actually rewrite this in terms of exponentials, because I've been thinking about them so much for the calculus course.
Cool. And I actually quite like this method because it doesn't require you to remember anything else. It's kind of just using the stuff you've been taught in the course. So I think there's a lot of merit in this. Maybe I'll do it my way. So my way requires you to remember. Remember the limit. You have to remember that this is the definition of E. And then you cube both sides. No, not cube both sides. I mean, you could cube both sides, but let's not do that. Let maybe I'll call this one. I might call this U. U. Okay. Equal to U over 3. Yeah. No, and I'm getting this all backwards. Then let U be equal to X over 3. Then lim. I'm getting all confused. Did I want to cube this?
No, I think you want the substitution.
I want the substitution.
If you're going to start with that fact, you want the substitution.
I've forgotten what I was going to do here. Okay, then the limit as x goes to u goes to infinity, x goes to infinity, then this becomes x goes to infinity of 1 plus u is, so it's just 3 on x. I think I might have been better off just cubing both sides, now that I think about it. Anyway, I'll just keep going with this. And this is x on 3. And this is still equal to e. And this is still equal to e. And then I can cube both sides. And now, because cubing is a continuous function, or since I can bring the limit outside the cube. And then I just multiply those things. Yep, I managed to confuse myself here, but it's arguable that this is not any easier than what you had.
I think it's a little bit cleaner. There was less writing in the end. It still came down to the same fact. You still have to use the fact that this function is continuous. Well, not maybe the quite same facts, but you have a continuous function. So you are only allowed to do this with limits when the functions are continuous at that point. So the cube was continuous at e, which is where this tends. So this works. But you do need to remember this fact.
Yeah, so my one has a bit more overhead than your method because you have to remember an additional fact.
Yeah, well, although for a lot of people this is a very natural fact. This is sometimes the definition. Yeah, I think in our course it's actually a consequence of our other definitions, but it becomes an equivalent definition of E.
This is the original definition of E.
Yes, I think this is the original definition. I think in our course we managed to it's the inverse of 1 under the... It's a special number. It's the function which gives you 1 under the inverse of a log function.
That's the traditional way to find it.
Yes.
All right, let's move on.
Right. Daniel will do this next question, and we did have to paraphrase it just to fit it on the sheet, but the information's still there. So it's the same information that's given in the test. The test is a bit more verbose in how we describe it.
Okay. I think is this the final question of the 1131 paper?
Yes, this is.
Okay, so this is kind of a meaty question. You have two planes, they are parallel and pass. So you're told they're parallel, and that one of them passes through the origin. But you could have, I mean, this is just the question being nice to you. You could have determined they're both parallel because they have the same normal A, B, C. And you could have determined that this one passes through the origin just by setting A, B, and C, X, Y, and Z to be equal to 0, and that being a point that satisfies the equation. So just to set up what's going on here, I'll draw us a kind of illustration of what's going on. Here's one plane, and maybe I'll draw a bit of an angle. Here's kind of one plane passing through the origin, and here's a kind of parallel plane. Find in parametric vector form the line passing through the origin which is perpendicular to both planes. Well, finding the perpendicular is not so bad. This is the origin here. And this is supposed to be kind of perpendicular, or normal to the plane. So just, this is a picture of what's going on. So for part A. Let's call this thing n. The normal is the vector a, b, c. And you can see that just by, you can convert this into parametric vector form, or if you're familiar with the Cartesian form of the plane, just read off the coefficients of x, y, and z. The normal is those coefficients, a, b, and c. So if you like, this vector n, let's add it to the picture, is this kind of purple vector. This is the vector n here. And we want the line passing through this passing through the origin, which is has the direction of n. Perfect. This is the line. It's passing through both planes. It's passing through both planes, of course, and it's normal to both of them. So here we have parametric vector form of the line. Here is a point on the line. Naturally, 0 is the point to choose, and this is the direction of the line. Hence or otherwise find the distance between the two planes. Well, now that I have this equation of the line, and I know this point, all I need to do is know this point. So really, I just want to intersect this line with the second plane to find this point. What do I know? So if I'm intersecting these two things, I could just substitute one into the other. X has the shape lambda A, Y has the shape lambda B, and Z has the shape lambda C. I said that all. No, that was correct. That was correct. I did that one right. All right. This tells me that A times lambda A plus B times lambda B plus C times lambda C is equal to D. So I should explain this. I know that this is a point on the line, and if this point is simultaneously on this plane, then x is lambda times a, y is lambda times b, and c is lambda times c, z is lambda times c, just by the equation of the line. So I can factor out my lambda here. This is lambda times a squared plus b squared plus c squared, and that's all supposed to be equal to d, so lambda is equal to d on so this is lambda. And hence I know what this point is. This is just going to be lambda, this lambda, d on a squared plus b squared plus c squared times by my normal vector. And now I just need to find the distance from here to here, which is the length of this vector. Huh. Josh.
So there is one thing I would maybe have to be careful about here. I don't think there was any guarantee that d was a positive number. So here, when you're taking the length of this vector...
Thank you.
Yes,
Thank
so,
you. All right.
that should work regardless of what d is. So you would have the right magnitude, but the wrong sign. So
Damn.
this number at the bottom is always positive, so there's no need to put absolute values there. But yeah, so that is the answer to this question. That is the distance between these planes. So almost perfect. Right, so we're going to move on to the 1141 questions we picked out.
Maybe I should mention that the diagram is really helpful here. I think you do need some kind of diagram to just help you understand where to put all the symbols, because otherwise you're just shunting symbols around in the dark, and that's no way to live.
Also, these questions that say hence or otherwise, usually hence would be the best option.
Yeah.
You could do otherwise, you could try and find your own method, but they were trying to set it up for you. They're trying to be helpful. Alright, so I suppose remember with the 1141 exam, your first two questions are the same as the first two questions in the 1131 exam. It'll be question 3 and 4, which are the different ones. That's why I'm starting with the question 3 question. So this is a bit of an abstract question. It wants you to sketch a function, and it wants you to make sure it's a function with these properties. So it has to be defined on the domain 0 to infinity. It has to have a vertical asymptote at x equals 0. And we want it to be increasing on the domain 0 to infinity. And then we'll actually try and think of a rational one which does this for us. But for our sketch, anything satisfying these three properties should be fine. So let me just have some axes. I'm only caring about defining it on the domain 0 to infinity, so I'll only draw positive x values. So vertical asymptote at x equals 0, I want there to be a function to shoot off to plus or minus infinity here. So it should either go up to plus infinity or down to minus infinity. But that's not really entirely my choice, because it has to be increasing. It has to be increasing on this entire interval, so it had better been coming up from minus infinity. So I'm going to draw a function which comes up from minus infinity. It's always increasing and just keeps going like that. So, I mean, looking at this, a classic function I could actually write down is the log function. Unfortunately, that won't help us with the second part. So this it is defined over the range 0 to infinity. It has a vertical asymptote here, and it's increasing. So this is a plot of y equals f of x. So that's a suitable graph. Now part B is actually to test whether you can actually construct such an example. Construct an example which does something like this. Now actually the example I think I will choose will not be looking exactly like this. I'll choose a slightly different example. And I'll try and iterate over my design to see what happens. And notice, you do have to justify that you do have these properties, so you will have to justify that this is a good example of this function here. So, the first guess, well, I want to have this vertical asymptote. I might just have a first guess at 1 over x. I mean, that satisfies 2 of 3 properties. It does have a vertical asymptote at x equals 0. It is defined over 0 to infinity. The only singularity, the only point where it's not defined is 0. But it's not increasing. In fact, if we know this function, we know it's decreasing. And the easiest way to get an increasing function is just to flip it over. So I claim this is a good example, and it's a good enough example to satisfy this. Let's justify that. So this, maybe I'll call this f of x. So this sat satisfies the requirements above. So let's just go through them one by one, since it is defined everywhere except x equals 0. That means it is defined over 0 to infinity as x tends to 0 from above. One over x tends to minus infinity, i.e. vertical asymptote at 0. And to prove it's increasing, well, let's just take its derivative and look at its value. And finally, since the derivative of f of x, the derivative of this is actually just 1 over x squared, and that is greater than 0 for x greater than 0. In fact, it's greater than 0 everywhere except for where it's not defined. This is always increasing. I'll be a bit more precise. It's always increasing where they want it to increase. So that's a perfectly good function. I think I've shown it does satisfy these 3 properties. Yeah, so any comments?
Looks good to me.
Yeah, so the design, you may not end up with the exact same function, but this seemed like a good one. 1 over x seemed like minus 1 over x seemed like a perfect good function.
How do you know it has domain 0 to infinity?
So domain, not range, just needs to be defined over 0 to infinity.
Good.
Well,
so it's not got a bigger domain?
It does have a bigger domain. There's no way you could have a rational function with a restricted domain like that.
Okay. So
it's not possible.
Right.
Rational functions are only not defined at single points, because they're not defined when the bottom goes to 0, and polynomials only vanish at points.
So something like square root 1 on negative 1 on square root x, would that be?
I don't think that counts as a rational function. So the question says rational, and to me,
I believe you.
Rational means polynomial over polynomial. Yeah. So I think this is what they want. Yeah, it's not possible to have this as the only domain for a rational function. That's just not possible.
I can believe that.
Yeah, I was wondering the same thing when I was writing this question up. I was thinking, there's no way to restrict that. So they must just be saying, at least defined over this.
Okay.
Maybe more.
I'm happy. Okay. So here we are towards the end of the 1141 exam, and things are getting a bit hard. So suppose you have two non-zero complex numbers with some argument restriction satisfying this. Part A, find z in terms of w. Well, the good news is this is just a quadratic formula. This is just a quadratic in z, so we can rearrange it and apply the quadratic formula. So for part A, z squared. So z is equal to w squared two, which is equal to w plus or minus root 3i w over 2, which is I can take a common factor of w out of this, and it's 1 plus or minus which I might choose to write in polar form as times e to the pi on 3i plus or minus pi on 3i. So complex number w times e to the pi on 3i, or times minus e to the pi on 3i. So z is just a rotation on w. It's a rotation by either pi on 3 or minus pi on 3. So I can draw a pretty picture of that. Here's my Argand diagram. Let's say, for example, this could be w, and z is supposed to have smaller arg. So maybe this one can be, let's make, no, damn it, here. Let's make this one w, and this one z. And this angle is supposed to be pi on 3. So that's what this is saying. Z is just a rotation by w on pi on 3. There's lots of ways you can show that ZW and the origin form an equilateral triangle. You could say that this angle, this length is the same as this length, and the angle between them is pi on 3, which is probably the fastest and therefore best way to go about it, since mod Z is equal to mod W e to the plus or minus pi on 3i is equal to the length of W times the length e to the plus or minus pi on 3i, which is equal to length W, since mod Z is equal to W and the angle is pi on 3, the triangle is equilateral. I can't spell equilateral. Okay, yes I can. I can copy it off what you wrote. There you go. Equilateral. You could also find the length between Z and W.
Jumping to my mind as a third option.
Yeah,
you could do know this length is you know the size of this number is W. When you work out the size of this formula will tell you it's also the modulus of W. You just need to show that the difference between here is also the modulus of W. So you'll need to look at W minus Z or Z minus W.
And it's fairly straightforward to do that. It's just a little bit, it is a little bit more more laborious. So or say length Z minus W being equal to length and you take a common factor of W out, and that's the length. And this this just ends up being W times the length of minus 1/2 plus or minus root 3 to I, which is, again, this is a complex number of modulus 1, so this is just the length of W again.
Yeah. So yes.
I think this is, I kind of prefer this because it shows a bit more kind of geometry of what's going on.
That's true. It does. You do need. Yeah, you do need to. You really need to get this number in polar form to work that out.
Yeah.
So if you didn't end up getting that number in polar form,
Then
this
this
might
would be
be
better,
your backup. Yeah. If you get into polar form, then it's quite obvious because yes, you have that pi over 3 angle, that 60-degree angle. Okay, so the. Oh yes, I didn't have time to write up the last question.
Oh, okay.
So I'll write it up now.
Maybe while you're writing it up, I could do another proof question.
Okay.
So here's a bonus question. From the tutorials, one of the questions asked you is, one of the questions is to prove that A inverse transpose is A transpose inverse. This is some question from the final chapter of your book on matrices. You have to prove something. Now, typically when you get asked to prove something, it's a bit weird because unlike something like finding roots of unity, you have no initial starting point. What you do have is the end point. Instead, you have the end point. This is where you have to land. So it helps to. It's a bit different to the kind of normal questions you get. You get told where to finish instead of being told where to start. Let's think about this. We're supposing that A inverse transpose is A transpose inverse. What that means is that if you want to take the inverse of A transpose, you could just take A inverse transpose. Well, let's see if this is true. If well, actually, this is going to be equivalent. This statement is equivalent to saying that A transpose times by this object is equal to the identity. This is the property of being an inverse. This matrix, if a matrix times some blob is equal to 1, or the identity matrix, then this blob must have been the inverse. This is exactly this is the definition of inverse. This blob is the inverse precisely when A transpose times blob is the identity matrix. Right? So, and this is something we can work with because since I can there's a transpose common to both of these. A transpose A inverse transpose is equal to A inverse times A transpose. Remember, the transposing swaps the order of the multiplication. Is equal to the identity matrix transpose, which is equal to I. Then this object here, whatever it is, must have been the inverse of A transpose. So the proving questions are a bit surprising because you don't necessarily know where to start. You have to think about it for a bit. And in this case, you need to know that this is going to be the inverse, which is what you're asked to prove, precisely when this occurs. And this is something you can actually prove because this simplifies to just this. Josh.
So yeah, I like this question. I mean, it's an interesting little fact. You do have to be careful to get this right, though. It would be very easy to forget how transposes actually swap the order of product. If you wrote that down the wrong way, you'll come to the same conclusion, but you would be wrong about how you got there.
Yeah.
And that could cost you.
Yeah, I would be looking for that if I was marking this.
Yeah, I'd especially be looking for that.
In fact, that may be the only thing I was looking for.
Right, so this is actually the final question we're going to do.
All right. Awesome.
So this may actually be they've actually introduced a new type of matrix to you in this question. It's something called a unitary matrix. It's somewhat similar to an orthogonal matrix, which I think you have seen. But rather than having that Q transpose Q as the identity, you have this Q bar transpose Q, which here Q bar is the complex conjugate. You take the entries of the matrix, you take their complex conjugate, and then you do them up, and then you take the transpose. Now, the first one's, well, it's in some ways it's not very hard. It's saying just give me one example of a 2x2 unitary matrix, but make it an interesting one. It has to have some non-real entries. And that may be hard if you haven't met these matrices before, so let's actually work out some conditions that will allow us to make our search a bit more efficient. So a good way to get control of these sort of things is to actually give them names. So let's write down a matrix Q and give it the entry some names. So let's let Q be the matrix A, B, C, D. Well, if I then look at Q bar transpose Q, so I might write in 2 steps just to be very clear. I'm taking the complex conjugate of all the entries, I'm transposing it, and I'm multiplying it into Q. So this is the matrix I'm writing down. In terms of rows, it's A bar, C bar, B bar, D bar, times A, B, C, D. And it's a fairly standard matrix product. We can just write down what this product will give us. So multiplying this row onto this column will give me A bar A, C bar C. So with A bar A plus C bar C. Next one is, well, A bar B, and then C bar D, get B bar A, plus D bar C, and this last one is B bar B, plus D bar D. And this is supposed to be the 2x2 identity. So I have some, this is going to give me some conditions to help my search. So I'm going to write down what these conditions are just so I can see them a little bit clearer. No, this is a complex number times its conjugate. That is just actually the square of the modulus. So what do we have? We're not going too low. So this first one has to be equal to 1. So I'm going to get the square, the modulus squared of this complex number, A, plus the modulus squared of C is 1. It's really telling me that I can't make these numbers too big and they can't be trivial. Let's actually look at this other condition first. The complex, let's see. So yeah, the modulus of B squared plus D squared is 1. Again, these numbers can't get too big, but they also can't be 0.
Don't go any lower than that.
Okay. And there are 2 more conditions, but if you look at them for a while, well, you can just write them down, both of them, but they actually turn out to be the same condition. So let's write them both down. It's A, B plus C bar D equals 0. And I'll write this one slightly differently to how it's here, to A, B bar plus C, D bar is 0. Really, this is the complex conjugate of the thing above. So I need to satisfy all these conditions, and I need to find some numbers which aren't I need to make sure that I pick a few numbers which aren't just standard real numbers. Let's plot this out. So if you've worked out these conditions, so well I just can't have both A and C being 0, but I could pick one of them to be 0 if I wanted, and that would make this condition a lot simpler. So what I could do, maybe I'm working on scrap paper doing this. Let's work over here. I'm going to let C be 0, for example. So if I let C equal 0, well then in terms of my condition, I don't have to worry about that, and I don't have to worry about that, or that. Well, I do need A to be non-zero, otherwise I'll never satisfy that. So this A can't be 0, but now I'm seeing that the B must also be 0. So let's let B be 0. That's gone from my condition. These are satisfied, and I don't. So I'm left with actually two conditions. I need that A must be a number whose modulus is 1, and D must be a number whose modulus is 1. And those are the only conditions I need to satisfy, so any complex number like that will work. So I might as well just choose, slipping into maple notation, I might as well just let A equal I. That satisfies that, and it's not a real example, not a real number. And D, well, let's just, again, I might just choose D equal to I as well. And this works, satisfies this condition and this condition. So those satisfy the condition, giving the example. So my example I'm giving is Q is equal to I, 0, 0, I. And actually this is just I times the identity. Turns out that if you look at this condition for a while, you'll see that the complex conjugate here on the I just makes it work very nicely. So once you have this example, I can actually think of a whole host of examples, which are maybe more interesting, but this is good enough. So it's a 2 by 2 matrix that has some non-real entries, and it does satisfy it is unitary. So I'm happy with that. Any comments?
Looks good.
Yeah. So I did have to slow down here just to make sure I didn't make my life impossible to begin with. It's too tempting to maybe make too many parameters 0, but you have to look at your equations, make sure you're still leaving a solution to find. And the next part, well, I think that actually might be easier than this first part, honestly. Finding the example feels like harder work to me. We want to prove a very general fact about these. We want to prove that the determinant of a unitary matrix is actually just a complex number of modulus 1. That's really what it says. This actually feels very similar to the statement you make about orthogonal matrices. You know orthogonal matrices have determinant 1. This is similar. Now I'm actually going to prove it in a similar way. So let Q be a unitary matrix. And the only thing we know about unitary matrices is that the conjugate transpose times Q is the identity. Well, what that tells me is that the determinant of this product is equal to the determinant of the identity. I actually think in the question they had one more condition about Q. Q is a square matrix. In the exam they did state it is square. So because this is a square matrix, well, when you take the determinant of a product, it is the product of the determinants. So I get the determinant of Q bar transpose times the determinant of Q. Well, determinant of the identity is always the same thing regardless. It's always 1. Determinant of a transpose. Well, determinant of a transpose is determinant of the matrix. And here's where maybe I need to do a little bit of thought. The determinant is actually a polynomial in its entries. So what I can do, if I'm taking the conjugate of all the entries, I can actually move that outside the determinant. So what may or may not be obvious is that this is the same as the conjugate of the determinant. If you're looking at Laplace's expansion of the determinant, so you look at that polynomial, you just actually conjugate everything in there. And I might write that reason down since the it's just a polynomial function in the entries of Q. So we just got this number, its conjugate, times this is 1. So this is saying, well, if you take a number, take the conjugate of a number times itself, this is just the modulus squared. So that means the determinant is a complex number of, well, of length 1.
Yeah, look, I think that's
Yeah.
fine. Cool.
So this is, maybe,
Sure.
I say that for instance.
Yeah, that's fine. So I remember marking this, and a lot of people did get this part with not actually doing this part. I do want to mention a couple of things. We've done what we think are the hardest parts of the 2016 exam. When I marked this, only a handful of people actually managed to get this successfully. So it's hard. This part is hard. And really the only reason those bits are in there is so we can give HDs to some very deserving few people. So if you're keen for the HD, then you need to be across this kind of stuff. If you just want to pass, then what you've seen in this video is going to be well above what you need to do in order to be able to pass. We're just trying to get at the meaty bits of the course. Second of all, there was a question in the forums about when do you need to actually prove stuff and show working. This is a kind of a good example of that. Part A just says, give an example of a 2x2 knot. You could just pull an example out of anywhere and write it down. You get the marks. You're just supposed to exhibit an example, right? You don't have to do any working. It's nice that you do have working, but you're not obliged to. This bit, you actually have to show something. You can't just state determinant is 1. Sorry, you can't just state its determinant has unit modulus. You actually need to do something to prove that. Cool. So you wouldn't be able to just state this. You'd actually need to go through some other steps to get there.
Yeah, so in the last question, I mean, if one popped into your head, an example like that, if you knew I times the identity was an example, you could just write the one down. The only reason I did it that way is if you do want to search for one, and you haven't thought of one, you have to do a bit of work. So your search may take a little bit of work.
Cool. Yeah, I think we're done. I'll post a link to last year's stream. We did a stream last year for the 2015 exam, so I'll put that on Moodle. I think that has some kind of gentler examples
yes.
in it.
I remember that being a bit less taxing than this one.
Cool.
Okay, cool. So good luck. Don't forget about, so the Maths Drop-In Centre is still open next week, and there's a roster of consultation times going up. Please make the most of the help while it's available.
Good. All right, and good luck with your exams.
Good luck.